Let's think about two familiar solutions, salt water and sugar water. They're similar, right? You take a household substance and you dissolve it in water, they look the same. They both dissolve, appear to disappear, and yet they do so differently. So what happens when a solute dissolves is we have to think about the different interactions that are occurring. There are solute-solute interactions, so between the ions in sodium chloride or between the sugar molecules in sugar. This is what causes that substance to be a solid at room temperature, is that there are forces of attraction holding the particles together. If there was no attraction, the particles would fly apart and it would be a gas. When we dissolve this in water or in a solvent, we can also have some interactions between the solvent and the solute. So these are called solvent-solute interactions. And then there are also attractions between the solvent molecules. Because the solvent, in this case, is water, it's a liquid at room temperature. Again, if there were no forces of attraction between the particles, they'd fly away and it would be a gas. So we have these three different types of interactions, and whether a substance dissolves or not has to do with the relative strengths and types of interactions between the particles. So if the attractions between the solvent and the solute are strong enough, the solute will dissolve. If the solute-solute interactions are very strong and these interactions are very weak, this will not come apart in solution. It will just sit there in the bottom and not dissolve. So we have to look a little bit at water and what it's like. So here's an illustration of a water molecule. Here's the oxygen, and here are the two hydrogens. The bond between oxygen and hydrogen is called a polar bond. The electrons are not shared equally. And so what happens is that there's an uneven distribution of electrons in the water molecule. The electrons spend more time around the oxygen end of the molecule and less time around the hydrogen end. And so this end is partially positive and that end is partially negative. It's not an ionic compound. The water is not oxygen ion and hydrogen ions just being attracted to each other. There is a covalent bond, but this end is a little more negative and this end is a little more positive. Any questions about that? Yes?
What do you mean by they spend more time on that side? Aren't they like spinning around really fast?
Well, we'll talk more about this later, but electrons are not in orbits around the nucleus like the planets are in orbit around the sun. And so they don't have a prescribed route that they travel. They technically they are wave functions, and so in a sense they're everywhere and nowhere at the same time. They're very it's quantum mechanics. It's mind-blowing. I think of it in terms of my children. So I remember one day I came into the living room and all 6 of them were sitting on half of the couch. I don't think it's ever happened since. It was just this random occurrence. Normally, they're just pretty much scattered throughout the house, or they're off at school, now they're off at college, they're scattered all over the place. But occasionally, they'll all clump up together for whatever reason. Electrons can kind of do that as well. And so the electrons that are shared in this bond between the hydrogen and the oxygen, we might think would just, be kind of distributed throughout the whole space. But the truth is that the oxygen is more attractive to the electrons. And so the electrons in that bond, they can be found over here, but they're found near the oxygen more frequently. And so we have a little bit of a negative charge here, not a full -1 charge. It might be like a 0.1 charge. It's just a small negative charge. And in this bond also, the electrons that are being shared between the hydrogen and the oxygen are near the oxygen more often than they are near the hydrogen. And so in terms of charge distribution, water is lopsided. Does that help? And we'll study more about that later, probably more than you really wanted to know. Yeah, this is a polar molecule because the ends of it are different. You think of the North and the South Pole, right? magnetic north and magnetic south. There's a distribution, a separation of magnetic charge. So with these kind of lopsided water molecules, when we put sodium chloride into the water, sodium chloride is an ionic compound. We have positive ions and we have negative ions. They are stuck together in the salt crystal because positives and negatives attract each other. When we put this into water, the negative end of the water molecule is attracted to the sodium ion, which is positively charged. The positive end of the water molecule is attracted to the negative ion. Now, just one water molecule is not enough to lure this chloride ion away from the sodium ion. That +1, -1 charge attraction is very strong. But if we got a whole bunch of water molecules, they can sort of, I think of it as luring the chloride ion away. Oh, come away with us. You'll be more comfortable. We'll surround you. We'll make you feel just as happy as you were with the sodium ion. And the water molecule is turning its other side to the sodium ion and doing the same thing. So here in this illustration, we see the positive sodium ion with several water molecules around it. And the negative end of the water molecule is attracted to the positive ion. That's a solute-solvent interaction. And because that is fairly strong, it can overcome the solute-solute interaction and pull those ions away. And then over here, we have a negative ion, and the positive ends of the water molecules are surrounding that. Again, we have good solvent-solute interactions that help to overcome the solute-solute interactions that were holding the ion together. So these ions then become free of each other. They're no longer attracted to these other ions, and so they separate and they can move freely throughout the liquid. Any questions? Yes?
Wouldn't that change the properties? Would it not taste like salt anymore?
Wouldn't it change the properties? That's a good question. In some ways, it changes the properties because now it's dissolved in the liquid. It's not a solid anymore. So in that sense, it's changed. But it's going to taste the same because when you taste salt, there is water in your saliva, and the salt is dissolving in your saliva, and you are tasting it that way. So it's actually going to taste the same. Yeah, that's a good question. We'll talk about this later as well. Solid sodium chloride does not conduct electricity, but sodium chloride dissolved in water does, because these ions are now free to move and they can carry electric charge. In the solid state, they can't move relative to each other, and so they cannot carry a charge and they will not conduct electricity. So electrolytes are substances that when you dissolve them in water, they will conduct electricity. These are going to be soluble ionic compounds. You've probably heard the word electrolyte in Gatorade commercials, right? You have to replenish your electrolytes. Yes, you do, because your body requires electrolyte solutions to function. And when you sweat a great deal, you lose some of your sodium ions and your potassium ions and other ions, and you have to get those back. So electrolytes, when dissolved in water, form a solution that conduct electricity. Non-electrolytes can dissolve in water, but their solutions will not conduct electricity. And this includes most molecular compounds. So when we dissolve sugar in water, it will not conduct electricity because sugar is a molecular compound. It does not separate into individual ions. For a solution to conduct electricity, there have to be charged particles that are free to move and carry the current. Electricity is a flow of electrons. If the electrons can't move, there's no current. So the salt solution conducts electricity, the sugar solution does not. This is, I will try to get this apparatus out and see if I can get it to work. I tried last semester and it didn't work. I don't know why. Something wrong with the apparatus. If you connect a light bulb to some sort of a voltage source and two electrodes and put them in just plain water, the light bulb will not light up, because in order for the light bulb to light up, this circuit has to be closed. There has to be electrical conduction between these two electrodes. When we put salt into the water, the salt dissolves, forming ions that are free to move, and it completes the circuit and the light bulb glows. If we do the same thing with sugar, however, it does not light up because sugar molecules cannot conduct electricity.
So why do we hear that, like we drop a hairdryer like in a tub or something?
That's a good question. What about, the stories about dropping a hairdryer in the tub? I mean, why would you want to dry your hair while you're still in the bathtub? But it happens. Or, a toaster in the bathtub or something. You can get a lethal electrical shock. But you're saying that plain water doesn't conduct electricity. Well, pure water does not conduct electricity well at all. Is the water in your bathtub deionized? No, it's tap water, which contains some dissolved minerals, and then your sweat is in there. And the other thing is that you've got a large voltage, 120 volts from the house outlet. And so high enough voltage source will conduct even by electrolyzing the water. So yeah, you do have to be careful around water and electricity.
But if we made the tub like a bunch of sugar water, would that cancel it out or not?
Adding sugar would not cancel out the effect of dissolved ions from the tap water and from your own sweat. Yeah. It would be an interesting experiment to do. There was a Mythbusters episode where they tried out this body in the bathtub thing. It was pretty interesting. You could try it with sugar and stuff. I would not experiment with my own self, though, or any actually living organism, because, what if you miscalculated something, right? That's a don't try this at home thing. Yes?
Are they still filming good episodes of Mythbusters?
I think they stopped.
This is the last season.
Yeah, I think I saw my kids watching it, and it was their farewell season. So that's a bummer. But there's lots of reruns to watch.
Oh, yeah.
We should watch them in
No,
class.
we should watch Bill Nye, the Science Guy.
Bill Nye the Science Guy is pretty awesome, too. So this is what happens when sugar dissolves in water. So here's a model, space-filling model of a sugar molecule. It's hydrogens and carbons and oxygens. And it is also polar. So we have the oxygen and the hydrogen here, and the hydrogen in this bond is going to be slightly positive, and it's going to be attracted to the negative end of the water molecule. And so we do have interactions between the solute and the solvent. And those are enough to break up the solute-solute interactions and cause the water molecules to dissolve. But these are neutral molecules, they are not ions, and so they do not carry charge. So a sugar water solution will not carry electricity. Salt water will. We've talked a little bit about acids. Acids are molecular compounds that ionize when they dissolve in water. So they dissolve in water and they form hydrogen cations, H+, and they form anions. They dissolve in much the same way that sodium chloride dissolves. The molecules are pulled apart by their attraction for the water. We have strong acids and weak acids. A strong acid is a strong electrolyte. It ionizes completely. So hydrochloric acid is one of these. When you put that in water, all of the hydrogen ions and chloride ions separate from each other, and you do not have the intact molecule anymore. That's a strong acid. In a weak acid, only a small percentage of the molecules ionize. It does ionize. It does form hydrogen ions. It has to. It's an acid. But only a small percentage does that. Hydrofluoric acid is a weak acid. And so it does form some hydrogen ions and some fluoride ions, but you also have intact hydrogen fluoride molecules in the solution. Acetic acid is another weak acid. It does form hydrogen ions and acetate ions. But as in this illustration, here's a hydrogen ion, there's an acetate ion. But most of these are the intact molecules, and that's characteristic of a weak acid. It only ionizes a little bit. A strong acid is a strong electrolyte. It will conduct electricity strongly. A weak acid is a weak electrolyte and conducts electricity weakly. So that's kind of what I just said. So here we have a comparison between non-electrolyte, such as sugar, forms no ions, no conductivity. A weak electrolyte will form some ions, and with the light bulb, what we see is it glows weakly. It glows just a little bit, telling us that there are some ions there, enough to carry some current, but not very much. And in a strong electrolyte, all of the particles separate into ions, and then the light bulb will glow strongly. Any questions? So we talked about sodium chloride dissolving in water, and the ions separate from each other. They're kind of lured and surrounded by water molecules. That process is called dissociation. They are dissociating from each other. Here's sodium sulfide. When that is dissolved in water, it'll form sodium ions and sulfide ions. Na2S, it'll form 2 sodium ions and 1 sulfide ion. They're going to separate. Yes?
I had a question about the strong and weak acids. Like, what makes the hydrogen chlorine a strong acid when it has when chlorine has a -1 and then chlorine also has a -1? But it's weak.
That's a good question. There are, depending on which list you look at, there are 6 or 7 strong acids, and all the other acids are weak. And so there are explanations for why HF is a weak acid and HCl is a strong acid, but they get rather involved. So for now, we're just going to say because. But most acids are weak. So this is a binary ionic compound. It's just got 2 monatomic ions. This is an ionic compound that has a polyatomic ion in it. The polyatomic ions stay together. These 2 ions, the sodium ions and the sulfate ions, will separate from each other, but the sulfate ion itself does not fall apart. The sulfate ion is a sulfur covalently bonded to 4 oxygens that overall has 2 extra electrons on it, and that stays together. So carbonate, cyanide, hydroxide, all of those polyatomic ions, when a substance dissolves in water, those polyatomic ions will stay together. So we've got separated ions when the ionic compound dissolves, and that allows electricity to be conducted. But not all ionic compounds will dissolve in water. Some of them do not. In very simple terms, we say that a compound is soluble if it dissolves in water and insoluble if it does not. Well, that's a simplification, because what if it dissolves just a little bit? What do you call it? Well, there's slightly soluble, but for the most part, when we say soluble, we mean that a significant amount will dissolve. Technically, even an insoluble compound will dissolve to a very small extent. Because what if 1 cation and 1 anion dissociate? That's some dissolving, right? Is it enough to matter for any practical purpose? No. And so we do call it an insoluble compound, but even those dissolve just a teeny tiny bit. So if we look at silver nitrate, put silver nitrate in solution, dissolves, separates into ions very nicely. Silver chloride, put that in water, sinks to the bottom of the beaker. You can stir it all day. It is not going to dissolve.
Are we going to go over why?
We will go over which ones. The why is actually quite complicated.
Okay, because I was doing my homework and I was having a hard time figuring out which ones would be soluble versus insoluble, and so that's why I was.
Yeah, it is hard, and there's a list. There's a list that we're going to learn. Yes?
So what would you classify soluble, more than half of it dissolves?
Well, everything has a solubility limit. So sodium chloride dissolves quite well in water. But if you keep adding sodium chloride to a cup of water, eventually you will get a saturated solution where you can't dissolve anymore. And the amount that does dissolve in a given amount of solvent is called the solubility. So solubility varies. And so the division between soluble and insoluble is kind of a gray area. So I guess we could say if you put some in the solution and you can see that some of it has dissolved, we would probably call that soluble. If you put it in and you stir it and it looks like the same amount is still there, we would call that insoluble. Even though in all likelihood a little bit of it did dissolve, but not enough to be significant. So with sodium chloride, it's going to sit in the bottom. Now, there might be a couple of silver and chloride ions floating around, but not enough, say, to make the solution conduct electricity, not enough to be an electrolyte. So how do we know? Here's your question. How do we know? It depends on a multitude of factors. A lot of them have to do with relative sizes of ions and the strength of attraction between the ions and how the crystals pack together. That's not a good method for predicting what will dissolve and what will not. And so what's proven to be the best way is just to experiment. Throw some in some water, see how much dissolves. Does this one dissolve? Does that one dissolve? And then keep track of the results of that. That's called an empirical method. You actually do the experiment and find out, does it dissolve or not? Based on empirical methods, these are what are called the solubility rules for ionic compounds in water. This is a general set of rules that allows us to predict the solubility of many substances. You do need to memorize this. It's going to take a little bit of effort, but it's not that bad. So let me show you how this table works. In the top, we have compounds containing the following ions are generally soluble. And then over here we have possible exceptions. So if it has lithium, sodium, potassium, or ammonium ion in it, it's soluble and there are no exceptions. All lithium compounds are soluble. All sodium compounds, all potassium compounds, all ammonium compounds are soluble. If it contains the nitrate ion or the acetate ion, it will be soluble, no exceptions. If it has chloride, bromide, and iodide in it, it's generally soluble, except if you have silver, mercury 1, or lead 2 ion. So if you have PbCl2, it's not going to be soluble. But if you have iron chloride, it will be soluble. And then sulfate compounds are generally soluble, except with strontium, barium, lead 2, silver, and calcium. So ideally, you would learn these that are generally soluble, and you would memorize the exceptions. Kind of a halfway point is, okay, if you didn't quite get the exceptions, but you memorized the first part, that's a lot better than nothing, okay? So aim for memorizing both of them, but at least get this column. The bottom part of the table, these are things that are generally insoluble, and they're exceptions. So hydroxide and sulfide compounds, generally insoluble, unless it's paired with one of these. Well, this is kind of redundant, because if you see it's got lithium, sodium, potassium, or ammonium in it, you know it's soluble, and so you don't even really need to remember that exception. The best way to use these rules is to start at the top and go down. If you've got hydroxide or sulfide with calcium, strontium, or barium, it's going to be soluble. That's for sulfide. For hydroxide with calcium, strontium, or barium, it's going to be slightly soluble. Now, depending on the situation where you're having to predict this, you may need to interpret slightly soluble as soluble, or you may need to interpret it as insoluble. And then we've got carbonate and phosphate compounds. These are going to be insoluble unless they're with lithium, sodium, potassium, or ammonium.
Why does it say then that the resulting compounds are soluble? Because when they
Those are the exceptions.
Okay.
Yeah. Question in the back?
Is there like a easy way to memorize this, or is it just one of those things you just memorize?
Well, there's kind of some patterns in here. lithium, sodium, and potassium are group 1 metals. And so they're all together over there in group 1. Where'd my pointer go? Chloride, bromide, and iodide are halide ions. They're in group 7A, but fluorine's not included. We'll find out that fluorine, being the baby sister of that family, gets left out of some things. In terms of exceptions, we find that silver and lead and mercury too show up. Well, silver and lead certainly show up a couple of places here. There's lead and silver. And the other ones that are common as exceptions are calcium, strontium, and barium. Those are group 2 metals. So there's some kind of generalizations there, but nothing as nice as all group 2A metals form plus 2 ions. It's nothing that hard and fast. The way you learn this table is by practicing predicting solubility. And so we're going to do that right here. Predict the solubility of nickel sulfide. So we've got nickel ion and we've got sulfide ion. And we're going to run through this list. We don't have one of those. No, no, no. Oh, sulfide. So sulfides are generally insoluble. This is nickel. We have to check if it's one of the exceptions. Nope, not an exception. So is nickel sulfide going to be soluble in water? No. So I'd put that as a solid. It's not going to dissolve. Let's look at magnesium phosphate. So we've got magnesium ion and phosphate ion, and we're going to go through the list. Those guys, not one of those, not one of those, no, no, no. Phosphate. Phosphate, generally insoluble. We don't have an exception, so that one's going to be insoluble.
So would it be a solid?
So it would be a solid as its state symbol, yeah. Solid, meaning it does not dissolve. How about lithium carbonate? Yeah. We come down here, lithium, bang, soluble. This will dissolve. We don't have to look any further. So if we had to put a state symbol on this, we would call it aqueous, because it will dissolve. How about ammonium chloride? That will dissolve. It is soluble. Any compound with ammonium in it will be soluble. You don't even have to go any farther. If you go through the list in order, you actually don't need this exception or this exception because you won't get down there. Because you'll come to one of those and you'll say, oh, it's soluble. So you really don't have to memorize those if you learn to do it in order. Any questions?
How do you predict a gas?
How do you predict a gas? That's a good question. We don't have a table for that. For the elements, you can predict from the periodic table looking at the color of the element symbol. On this table, if it's red, it's a gas at room temperature. Some things we expect you to remember, like carbon dioxide and carbon monoxide, are gases at room temperature, but for the most part, there'll be some clue if you need to predict that. The solubility rules won't help with that. Ionic compounds are not going to be a gas at room temperature, because ionic compounds have very strong attractions between the positive and the negative ions, and so they're all going to be solids at room temperature. Any other questions?